three-dimensional problems in EMAT subject. Let's take a look at the overview of three-dimensional problems. First of all, we shall recap on Pythagoras' theorem, trigonometric ratios of acute angles to calculate unknown sides and angles in the right-angled triangle, trigo ratios of obtuse angles, the sine rule, the cosine rule, and this time we take a look at area of triangle using half AB sine C. Then after looking at the recap topics, we shall master the ability to apply trigo concepts to solve simple practical problems in three-dimensional, including those involving angles of elevation, depression, bearings, and we need to be able to visualize the relevant triangles and lines present in the three-dimension figures. So let's recap on the basic trigonometry. Okay, first and foremost, as what we have seen in the previous webinar, Pythagoras' theorem is one of the useful tools that we can use to find one of the given sides of a right-angled triangle if we know the other two sides. Basically, the square of the hypotenuse is equal to the sum of the squares on the other two sides. And then we have our trigo ratios of acute angles. In short, we call them as torcaso. And we can find the unknown angles and sides of a right-angled triangle using the tor, ca, and so. Then we also briefly mention about trigo ratios of obtuse angles. The relationship is such that sine of the acute angle is equal to sine of the obtuse angle. Cos of the acute angle is equal to negative of the cos of the obtuse angle. Then after that, we talk about sine rule. For sine rule, it applies to any kind of triangles, and we make use of the ratio of the side and the opposite angle. For example, we have A over sine A, so we have A over here, sine angle over here, sine A, and that is equals to B over sine B, as equals to C over sine C. The sine rule is used when there are any two angles and one side, or two sides and one angle that is opposite to one of these sides. And then we have our cosine rule. Our cosine rule again applies to any kind of triangle ABC, and states that the A square is equal to B square plus C square minus 2BC cos A. In other words, if you are given any three sides, we can use the cosine rule. If we have two sides and include the angle, which means it's the angle that is sandwiched in between the two sides. For example, angle A, sandwiched in B and C, that is the included angle. So we can use the cosine rule. Then of course we also need to find the area of a triangle. In the past, for area of triangle we use half times base times height. That is provided we have the perpendicular height with respect to the base. For this particular calculation using half AB sine C, there is no need for a right angle triangle. We can use this technique to calculate the area of any kind of triangle provided we have the two sides followed by the angle that is sandwiched in between it, which we call it the included angle. Then after that, we have some quick tips as a reminder for students to make sure that they do not create mistakes in trigo topic. First is always to check that the calculator is set to degree mode. Second of all, if the does not specify the degree of accuracy, Make sure that the non-exact answers are correct to 3 significant figures. Workings are always correct to 4 significant figures or more. Non-exact answers for angles are always corrected to 1 decimal place. We use Torcaso to solve right-angled triangle question, but we always use the sine rule, cosine rule, or half AB sine C to solve non-right-angled triangles. Now let's take a look at some three-dimensional problems. There are some terms that the student needs to know for three-dimensional problems. The first term is called plane. The meaning of plane means is any kind of flat surface like the surface of a table. It has only two dimensions, or sometimes in short we call it 2D, which we actually measure in terms of length and the breadth. And the second kind is just solid. Solid means it has three dimensions. What it means is we have the length, we have the breadth, and we have the height, which is the thickness. Okay, so this is what is known as solids. And then there's another one that is quite important to know is normal to a plane. Sometimes questions will actually mention about normal to a plane. What does that mean? It means that it is a line that is perpendicular, means at 90 degrees, to every line on that particular flat surface. So later on, we'll take a look at some more examples that talks about normal to a plane. There are some strategies to solve three-dimensional problems. There are three steps or three general steps to handle 3D problems. The first step is we need to reduce the three-dimensional problem to a dimensional plane problem, means something that is on a flat surface. And how we do that is we look for right-angled triangles in the relevant planes. The next step is draw the right-angled triangle that was being identified from step 1 that contains the length or the angle that needs to be found. And what is most important at this point in time is to label the triangle clearly. The third step is to apply Pythagoras theorem or Torcaso to solve for the unknowns, since we are already dealing with a right-angled triangle. So let's take a look at the first example. First example is quite a straightforward question. We are given the A, B, C, D, E, F, G, H is a cuboid. We need to find the length of AC. We need to find the length of HC. We need to find the angle ECA. So let's take a look at each part individually. For the first part, we need to find AC. If you look carefully at the diagram, AC is a blue line that joins point A to point C. So in other words, it's going to be a diagonal of the flat plane at the bottom. So what you can do is we have identified the plane which lies in the same manner as ABCD, and therefore we have identified the right angle triangle. In this case, it's actually ABC. Step number 2 is to draw the right angle triangle that was being identified earlier on. So this is actually the right angle triangle that we have. Now what we do is, since we have a right angle triangle and we label in the things that we already know, which in this case would be the length of BC, which is 5 cm, and the length of AB, which is 7 cm, we can easily use Pythagoras theorem to find the length AC, which is required in this question. And when we do that, we end up having a square root of 74 after the addition of the square of the sides. And in order to find AC, we've got the square root, that's 74, to get the answer, which is corrected to 3 significant figures because it's not an exact answer. Now let's take a look at the next part of this example. The next part of this example is we need to find HC. So as you can see in this diagram, HC is actually the diagonal of the back plane that contains HGCD. So we have these 2 points over here where the length H, and if you identify it correctly, you actually have a plane that is behind, which is GCD. So step number one, we have already identified the plane where it contains the length HC, and step number two is to draw the right angle triangle that we have identified earlier on. So this right angle triangle is actually HDC, and then we do know that DH has a height of 4 cm, CD has a length of 7 cm. So are we able to find the length HC? The answer is yes. Again, we make use of Pythagoras theorem because we are dealing with a right angle. So the answer works out to be square root 75. Square root 65. And our final answer is 8.06 cm, bracket 360. Finally, for this particular word example, our next task is to find an angle. And this particular angle is angle ECA, which works out to be this angle here. What we do is we are going to make use of trigo ratios of acute angles, or in shorter form it is 12 Paso. So we have already identified that in order to find this angle, we are going to have a plane that is in EAC. And when we extract that two-dimensional triangle out from that plane, this is how that right angle looks like. So our right angle triangle EAC has a height of AE as 4 cm. We have a length of AC, which was calculated earlier on in the previous question, as 8.6023 cm. So what we do is, if we need to find the angle ECA, we just need to make use of TOA, which means we need to have opposite over the adjacent, and then when we do an arctangent, we'll be able to find the angle of 24.9 degrees. Okay, so this is how we actually find the required angle in a right angle triangle. Okay, let's take a look at work example number 2. This time, work example number 2 is a bit more complex compared to work example number 1, because they now show you some other figures other than something that contains straight lines. So this diagram actually shows a cylindrical container with a circular base of diameter 22 cm, height of 30 cm, and we are told that M and N are the midpoints of AB and CD respectively. We need to calculate what is BC, you need to calculate what is BN, and you need to calculate what's the angle A and B. So let's take a look at this diagram carefully. So we have a cylinder, the diameter is 22, so which means C and D is actually diameter, A and B are also diameters, which means it passes through the center of the cylinder face, or not at the bottom. So our first task is to find BC. So I'm going to join B and C together, which is denoted by the blue line. So what we do is we are going to make use of Pythagoras theorem to solve our question. Why? Because we are able to extract a two-dimensional angle triangle out from given points on the plate. So we have triangle CDB, which is actually a right angle triangle. CD is actually the diameter of the cylinder, so it's given as 22 cm since the line CD passes through the midpoint of the cylindrical face. Then if we look at the distance BD, okay, BD has a height of 30 cm, and that means we are able to find the other side BC, because we already have two sides that is known for this particular right angle triangle. So it works out to be 7.2, which is in 3 significant figures, and then that's the answer. The next part of the question says we need to find Bn. If you look at Bn, this time B is connected to the center of the circle. So we have B over here, we have N over here. So what we do is we are going to join the points together to look for a plane that is on. And it so happens that this plane is actually the plane that cuts through the center of the cylinder. And then if you look at it carefully, it's a right angle triangle. So this is the right angle triangle is being identified. It has a base of 11 cm, it has a height of 30 cm. We need to find a length. So in order to find a length, it's not so difficult because as long as you have a right angle triangle, you can actually use Pythagoras theorem to do the job. So by substituting the relevant numbers in, your answer for Bn works out to be 32.0 cm. Now let's move on to the next question. The next question says we need to find angle A and B. A and B is essentially this angle over here after joining the points together. If we look carefully at this particular angle, we can see that triangle ABN is actually symmetrical. In other words, it's actually an isosceles triangle, which means two sides are equal. This edge and this edge are equal. And that means I could actually find the angle of half of it first using a right angle triangle. And after that, I just need to multiply by 2 in order to find the required angle. So what I'm going to do is, step number 2 strategy is to draw the right angle triangle out. So when I drew the right angle triangle out, I put in the details that I know. AM is actually 11 cm, which is actually the radius of the circle, because M is right in the middle of the circle. So therefore, it's the radius, 11 cm. And the height of MN is 30 cm, which is provided in the question. So what we do is we make use of Torcastle. So in this case, it's actually tangent. And so with tangent theta, we're able to find what is the value of the angle. So in this case, the angle works out to be 20.1363 degrees. But because we are looking for twice of the angle over here, so what we do is we just need to multiply by 2. You notice that the angle is not rounded off during the working. It is still in its form that is not being rounded off. And then what you do is you take that value multiplied by 2. It is very important that you do not use a rounded off value when you are actually doing your calculations, because if you use a rounded off value, your accuracy will not be there after you get your final answer. So in this case, you take 2 times of the angle and you end with 40.3 degrees corrected to 1 decimal place for angles. So that is our question for work example number 2. Okay, the next part is we need to take a look at work example number 3. Work example number 3 is very complex because you have many parts that relates to this question. And then this particular work example number 3 is actually a typical examination question that gives you different parts that require you to make use of the different concepts of trigonometry to actually solve for the answers. The first 2 parts, which is part A and part B, you notice that the question is highlighted in blue and italics. Reason being, this is the exact same question that was actually previously in the previous webinar on angle of elevation and angle of depression as well as bearings. So I'm not going to repeat that portion because today's focus is actually on 3-dimensional problems. But if you look at part C and part D, that is exactly what the question is trying to do. It's going to a 3-dimensional situation so that you are able to solve for the unknown. So let's take a look at part C. For those parts whose answer has been written calculated, they actually put into a diagram so that right now we can actually focus on part C and part D to solve the question. Let's take a look at part C. You have an yellow plane that is actually 10 kilometers vertically above W, and you need to calculate the angle of depression of the point Z from the aeroplane. Can you notice that this is actually a three-dimensional problem which makes use of angle of elevation and angle of depression. So since the aeroplane is 10 kilometers vertically above W and we need to find the angle of depression to point Z, what we do is we add in information into the existing drawing. So what we do is we actually indicate where the aeroplane is, which is 10 kilometers above the point W. Okay, so what we do is we assume that the plane is at that position. Alright, so the distance is actually 10 kilometers from W to the aeroplane. And then how do we actually find the angle of depression? You just need to join a point from the aeroplane to Z that will actually give us the angle of depression. Because this angle over here, that the horizontal line makes with the line of sight, that is actually the angle of depression. So if this is the angle of depression, it means that this angle got to be the same as this angle right here because of alternate angles. And then what we need to do is we need to draw the triangle out. It's seen over here. And then label the things that is already known and provided for and the things that is not found. So in this case, we know the height is 10 kilometers, we know the distance is 20 kilometers. We can simply use Torcaso to do the job because Torcaso is meant for right angle triangles whose angle is actually acute. So basically, you are able to find the angle of depression, which in this case corrected to one decimal point is actually 24.4 degrees. Okay, now we have the next one, part D. What D says we need to find the area of the field WZY. So WZY is actually this field over here. And then what we do is, if you look carefully, we are given all the three sides and we also have the angle, which was calculated earlier on in the previous parts. So remember, given three sides and an angle, we can easily apply what you call the cosine rule. Sorry, not the cosine rule. Cosine rule is to find the angle, which was found earlier on. We can easily find the area of triangle using half AB sine C. Okay, so in this case, we have two of the edges, which is 15 kilometers. We have the other edge, which is 10 kilometers. With the angle that was found earlier using the cosine rule, we can easily calculate it by using half AB sine C. So this is the formula that was used. And then when you actually apply it in, you'll get the answer. And remember, this entire question is actually given in terms of kilometers. So if everything is in kilometers, your answer for an area has to be in kilometers squared. So that is how you find the area of the field WZY. Okay, let's take a look at the next example. What example 4? What example 4 gives a diagram that looks three-dimensional. Okay, and you're given a series of information. And if you notice this question carefully, it includes knowledge that we have seen earlier on regarding angle of elevation and depression. We have seen things about bearings, and then this time now is three-dimensional. So it's actually a combination of the various topics that has been covered earlier on. So this question says, city stands at point A due east of a vertical flat pole. So this question is actually due east. And then what happens is the flat pole is OF. And it was observed the angle of elevation of the top of the flat pole F is 23. And then you're told that city walks 123 meters due north. So she walks from point A to point B. And then from point B that she's standing on, the angle of elevation to the flat pole turns out to be 12 degrees. So your task in this question is to find distance OA and the height of the flat pole. Okay, so based on strategies that we have looked at earlier on, strategy is to identify the plane as well as the triangle involved in that plane. So the triangle that is involved in this plane is OAF. So we focus on this plane first. Then after looking at this plane, we need to identify some more planes. Because by looking at all this information, it is not going to help us in the calculations directly. So nevertheless, let's take a look at the second plane that we have in this question, which is FOB, which is triangle that is behind. So once we have angle FOB, the angle of elevation is given as 12 degrees. But again, based on this information, it is insufficient to help us find our answers. The third triangle that you must be able to identify as a right angle triangle is the triangle that is at the bottom. In this case, it is triangle OAB. Even though a triangle OAB, the portion that says 90 degrees is actually angle OAB. Okay? Angles OAB, this part over here is actually a right angle triangle. So therefore, we can also put in another piece of information that we know, and that is AB as 123 meters. Okay, so this particular diagram actually combines all the three right angles together. And I hope you are able to visualize how the triangles are connected to each other. So now our question is, we need to find distance OA. But if you look at the first triangle that we have, yes, we need to find OA, and we are given an angle. How are we going to find the distance OA? So the thing is, there is insufficient information based on this right angle triangle. Since there is insufficient information in the right angle triangle, we are going to make use of whatever information that is available to us. So let's take a look at the first triangle. Okay, the green triangle has an angle of 12 degrees. In other words, we are able to formulate an equation that involves our distance, or OF, which is actually the height of the flat pole, the distance OB, put by tangent 12. So, and we label this as equation number 1. Next step, we actually do the same thing for the triangle that is nearer to us. That is going to be highlighted over here as equation number 2, which is given as OF equals to AA tangent 3, while the previous one is OF equals to OB tangent 12. So we have two equations and two unknowns over here. Okay. In fact, there are three unknowns. Sorry, there are three unknowns. We have OF, we have OB, we have OA. Two equations with three unknowns. We are not able to actually solve it because we don't have enough equations. But nevertheless, we can actually put equation 1 and 2 together because they are all OFs and equate them and come up with a relationship between OB and OA in the third equation. So we name it as equation number 3. So after that, what we do is, once we found the relationship that we have, we can make use of Pythagorean to help us connect the relationships. So the triangle that we're concerned with is actually the blue triangle that was at the bottom earlier on. So from here we can easily find what's the distance OA. Why? Because we know the relationship between OB and OA. We can easily substitute this equation into the Pythagoras theorem. And then what we get is actually the distance OA. So once we're able to find the distance OA, the next part should be quite simple. Okay, and the next part is of course to find the height of the flagpole. So all we need to do is to look for the equation that comprises of the height of the flagpole as well as the distance OA that we have calculated earlier on. Okay, so we substitute it into the equation and we get the height of a flagpole as given. So of course we have to correct these 3 simple figures, which is actually 30.2 meters. Okay, so you can see that we have looked through a series of work examples starting from the simplest to the complex question. So let's do a quick recap on what we have in 3-dimensional problems. Step number 1 is we need to reduce a 3D problem into a 2D plane problem by looking for right angle triangles in the relevant planes. Alright, so it has to be a right angle triangle and it must be in the relevant plane that we are looking for. Next one is step number 2. Step number 2 is after you have identified that right angle triangle in the plane that you are concerned with, you just need to redraw this right angle triangle and then you actually put in the information that you are provided with. Because once you have put in the information for the right angle triangle, that should help you solve using any of your Pythagoras theorem or Picasso to solve for the unknowns. Okay, so these are the 3 strategies to solve 3-dimensional problems in EMATH. So it's very important for you to remember how the strategies work. But the reason why it's important for you to be able to apply strategy because 3-dimensional problems can be quite difficult to visualize. Okay, so since it's difficult to visualize, we try to look at 2-dimensional figures which are much easier to visualize. Okay, so with this strategy in mind, we have actually come to the end of the webinar on 3-dimensional problems. Alright, and the next session is actually on question and answer. Okay, so if we do not have any questions, we have come to the end of our webinar on 3-dimensional problems. Okay, and we shall see each other again soon. Thank you and bye-bye.